3D rigid body equilibrium. In this section, we're going to expand on what we talked about in the last section with 2D rigid body equilibrium by bringing into the third dimension. So our objectives are going to be largely the same. We want to be able to draw a correct and complete free body diagram for a 3D rigid body, and in this process be able to correctly identify the types of reactions that all of the supports are going to impart on our object of interest. Using this free body diagram, we're going to be creating 6 equilibrium equations, 3 force equations, 3 moment equations to solve for these reactions. And then we're going to be solving these equations simultaneously to get numerical values for all of the reactions on our body. Like we saw for particle equilibrium and for 2D rigid body equilibrium, part of the requirements for static equilibrium is that all linear accelerations are 0. So here in 3 dimensions, we need to guarantee that our linear acceleration in the x, the y, and the z direction are going to be 0. And continuing what we saw for the 2D rigid body equilibrium, our angular accelerations must all be 0. So what's going to be new now is that in contrast to 2 dimensions where we could only potentially have an angular acceleration around that z direction, in 3 dimensions we have to worry about having our angular accelerations around the x, the y, and the z axes all be 0. So because of these requirements of all linear and angular accelerations being 0, this is going to necessitate 6 equilibrium equations when we have 3D rigid body equilibrium. 3 of these equations, the force equations, are going to look almost identical to what we saw for 3D particle equilibrium when we sum forces along the x, the y, the z axes. And we're going to have 3 scalar equations just like we had for the particle equilibrium. So what's new is to get the other 3 equations, we're going to take the moment around some point, here I'm just calling it generically q, and we have to ensure that that is equal to 0. But notice the way I'm writing this, this is a vector equation. Because when we take the moment about a point, it's always going to be a vector quantity. So whatever point we choose, when we take the moment about it, we're going to set it equal to not just 0, but the 0 vector. So keep in mind that this 0 vector is 0i plus 0j plus 0k. So this one vector equation actually is 3 scalar equations because after we write it all out, we're going to individually be able to say that the I component of the left-hand side is equal to the I component on the right, the j on the left and the j on the right, the k on the left, the k on the right. So this is actually 3 scalar equations totaling 6 linearly independent scalar equations once we get them all written. This point Q can be any point we choose on the body or off of the body, and it's still going to give us a unique set of equations no matter which one point we select. So even though we can always get the right answer, mathematically, arithmetically, it might be easier to take that Q around one point versus another. So in 3 dimensions, for example, if we have a ball and socket joint or if we have a fixed connection, which we'll be covering in a little bit, that is arithmetically going to make it easier to write out those equations and solve those equations. But again, we don't need to worry too much about what point we use, as any point will give us that set of 3 equations that will complement the 3 force equations in order to solve the problem. And just as a reminder, since in 2D we only ever get k values for the moment, in 3D we are going to get I, j, and k values in our moment equations. So we have to make sure that when we first make this one vector equation, it has the i's, the j's, the k's in it. Then we're going to split it up into 3 scalar equations where we're just picking off the coefficients. So after it's being split up into those 3 equations, the i's, the j's, the k's disappear because we're just equating coefficients. Because we are looking at equilibrium, we are going to need a free body diagram for this 3D rigid body. So once again, this is going to build on what we already saw for 3D particles and what we already saw for 2D rigid bodies. We must select our object of interest that we're going to isolate, and we're going to disconnect it in our picture from all of the supports it was connected to, be they ropes or a ball and socket or pins or hinges. Those pieces are not included in the free body diagram. Now we will see from once we get to more complicated types of rigid body problems, there might be different options for what we select as our object of interest, for things we want to keep stuck together or things we might want to separate. We'll see more of this as we get into frames and machines and friction type of problems especially. We need to establish and explicitly describe our right-handed coordinate system so that we know when we get to the i's, the j's, the k's, or summing forces in x, y, z, what the x, what the y, what the z axis is. All forces, whether they're applied or if they're reactions, and couples, whether they're applied or they are reactions or externals, need to be labeled, and they need to have either their numerical value or a variable name if we don't know what it is. Making sure that forces are going to be designated using a single arrowhead and couples either with a double arrowhead in the direction of the axis that the moment is about, or a curved arrow around the axis that the couple is acting. The two options for displaying couples is going to depend on how complex your picture is. You really want to be clear about which axis a couple or a moment is acting. Sometimes that's easier with the double-headed arrow, sometimes that's easier with the curved arrow. And we need our dimensions. Again, we're working in 3D, so putting down coordinates of points is going to be typically very helpful, and that's going to make the process of finding unit vectors easier, to find distance or displacement vectors easier as well when we have to take a cross product. But if appropriate, angles, ratio triangles could also be included, and because we're taking moments, we need to know distances. Lengths of different segments of our object of interest are going to be useful as well. Although the lengths, the angles, the ratio triangles, all of that is pretty much taken care of if we include coordinates of key points.